Welcome grade 12s. This is physical science. My name is Gillian and we are continuing to look at acids and bases. This is our consolidation lesson, and so we're going to have a look at our theory of acids and bases and how that all connects to chemical equilibrium and how we can use that in calculations and answering questions. So on my screen I have the overview, which you've probably seen before with big ideas. But what we want to really look at now is the pH scale. So we want to have a look at that and how we ask those sort of questions. And then neutralization is something that comes up often, particularly when we are trying to solve problems using our knowledge of stoichiometry. So this is quite tricky, it can be quite tricky, so we need to know our facts really well. So let's have a look at our first question. Question 1 is about ethanoic acid. Now, it says ethanoic acid, and they give us the formula for ethanoic acid, is an ingredient of household vinegar, and that should give you a heads up. So this is vinegar, acetic acid, or ethanoic acid is the same as vinegar, and we should know it as a weak acid. What does that mean? A weak acid is a substance which does not ionize completely. It really prefers to be in the molecular form. And that's actually the first question that says, is ethanoic acid a weak acid or a strong acid? And so we're going to say it is a weak acid. And what reason are we going to give? Well, we need to say that in particular this acid, so you can either use the formula or you can use the name ethanoic acid, does not ionize completely. So it does not ionize completely. We could also say that it has incomplete ionization. Okay. So that is what distinguishes a weak acid from a strong acid. A strong acid, of course, ionizes completely. And so there's very, very, very little molecules left in a solution of a strong acid. The next question is, an ethanoic solution has a pH, right? This is the first time we're coming up with pH, and it is at a very specific temperature, 25 degrees Celsius. We'll come back to that. Then calculate the concentration of hydronium ions, which is this ion here, H3O plus, aqueous in the solution. Now, this gives me the opportunity of walking you through this pH scale. So let's have a look at this. So when we look at the pH scale, it's a scale to place substances in terms of their H plus content. That's what this H is talking about. So how much of that ion is present? And to get a standard, water was used. So water is considered to have a pH of 7. So there is an auto-ionization of water, that reaction, where the water can act as an acid and as a base. So let's have a look at this. We see that we have the hydroxide ions and the H3O plus ions that are being produced in this reaction. So one of these water molecules is going to act as a donor, and I'm just going to take this first water molecule. Oops, it's a bit skew. And that water molecule is going to donate a proton, a H plus ion, to the second water molecule. That makes this one the acid because it is a donor, and it makes the second water molecule a base because it is accepting that proton. So here we have, in that process, we then have the hydronium ion, which is this one here, and the hydroxide ion being formed. You can see that our arrows are showing that there is chemical equilibrium and that the chemical equilibrium prefers the reverse reaction. So this very few water molecules actually react with themselves to form these ions. The water molecule prefers to be in the molecular form and not the ionic form. And that is why the reverse reaction arrow is bigger, longer than the forward reaction arrow. But out of this, we can calculate the Kc. Now, you've heard about the Kc, the equilibrium constant, and that is, I've written the formula here. It is the concentration of the product ions, so the hydronium ion and the hydroxide ion. So the concentration of those two times together divided by the concentration of the water molecules. Now, the water molecules will have a concentration of 1 because they are in the liquid form, and so they don't impact this formula. And we end up with a formula that is just the concentration of the hydronium ion times the concentration of the hydroxide ion. We call this Kw. Okay, because we're now working with water. So it is the equilibrium constant specifically of water. And it has to be at this temperature because our equilibrium constant is changed with temperature. It's the only thing that changes the equilibrium constant. So this has to be at a constant temperature. We end up with an answer of 1 times 10 to the minus 14. Now that minus 14 is telling you that that ion concentration in a solution is very, very small. It's little. Because we are going to have an equal number of hydronium ions to hydroxide ions, we can say that the concentration of the two is the same, and it will be 1 times 10 to the minus 7. Now, these are inversely proportional. That means that if the hydronium concentration decreases, the hydroxide concentration is going to increase by the same amount. Okay, so that's what's going to happen. If the one decreases, the other one is going to increase. How do we end up then with this scale? Well, we find that water, when we have equal number of ions, is 1 times 10 to the minus 7. And if we use a logarithm to change that around, and here it is here, we will find that if we take the hydronium ion, that the pH is going to equal 7. So this is a really important formula for changing a concentration into a scale, into a number that we can work with. And there's the logarithm. Now, when we speak about the ionization constant, the ionization constant is when we're talking about acids that are ionizing in water. We have a Ka value like that. Okay, so it's the ionization constant. When we're talking about something which is dissociating, it's invariably about a base, and so its Kb is going to be the constant for the base, the equilibrium constant for the base. We call it the dissociation constant. If we've got a strong ionization happening, complete ionization, then our answer there, the ratio is going to be greater than 1. And if we have a Kb value which is greater than 1, then we know that our ionization is happening to completion. We're dealing with a strong base. Grade 12s. Let's get back to our question. So we are given a pH of 3,85 at this particular temperature, so that we know that we're dealing with an equilibrium constant at the correct temperature. Calculate the concentration of these hydronium ions in solution. We're going to use that equation that we have just seen. So it is the logarithm, pH is equal to minus log of the concentration of the hydronium ions. We know what the concentration is we know what the pH is. It is 3,85, so we're going to substitute that in. And we're going to, on our calculators, do our logarithm working out, and we end up with an answer of 1,4 times 10 to the minus 4 mole per decimeter cubed. Now, concentration is mole per decimeter cubed, but have a look here at that exponent to the minus 4. So that is telling us that that it's a little bit. There is not a big amount of ionization. If there was a big amount of ionization, then that would be to the power of 0 or 1 or 2 maybe, and then we minus 2, minus 1. And then we know that our pH is 0, 1 or 2, and we're dealing with a strong acid. But we're not dealing with a strong acid. This is ethanoic acid. It is a weak acid. It ionizes incompletely, and so this number here is correct. Minus 4 to the minus 4, and it shows us in our pH value, so that's 3,85. It means that we haven't got such a strong acid. The pH is closer to 7 than it is to 0. Let's move on to our next question. Sodium ethanoate, and here's the equation as the formula for it. That is the negative part of this compound, and that is the positive part. Forms when ethanoic acid reacts with sodium hydroxide. So ethanoic acid, we know, is a weak acid, and its formula is going to be CH3COOH. There we go. That H plus tells us that it is an acid. Sodium hydroxide, we know, is a strong base, and its formula is NaOH. Now, this is the salt. Sodium ethanoate is the salt that forms when we've got this weak acid reacting with a strong base. The question is, will the pH of the sodium ethanoate solution be greater than 7, less than 7, or equal to 7? Well, we know that we have a weak acid and a strong base. There's no ways that our pH can be 7. Why? Because to get a pH of 7, we need a strong acid and a strong base. And then the resulting salt is going to have, it's going to be a neutral salt that is formed. Our solution will be neutral. So we're going to have to cross that one out. That one's not going to work. So now let's look at our weak acid and our strong base. If we have those two reacting together, we're going to end up with a salt that is slightly basic. Slightly basic. In other words, the pH is going to be a little bit more than 7. Not a huge amount more, just a little bit more. So our answer here is it's going to be greater than 7. It's time for a break. When we come back, we're going to have a look at the chemistry of why this pH is greater than 7. Welcome back from the break, grade 12s. So we have just said that when we have neutralization, a neutralization reaction of a weak acid and a strong base, the salt that results is going to be slightly basic. So now we have to prove or write an answer to why. Why is this happening? So this question, 1.1.4, says, explain the answer to question 1.1.3 with the aid of a balanced equation. Right, so I've written down what's happening in our reaction flask. So we have got this salt, this sodium acetate that has formed, and it is going to break up into its component ions, and there we've got the one ion there and the sodium plus ion there. This comes from a weak acid. So this part comes from a weak acid. That means that its conjugate base is going to be strong. So this is a strong conjugate base. Right? That means that this ion is going to be hungry for protons. So it is going to be really keen to pick up this proton here that is available from the water, the ionization of water. And so how can we show that in our balanced equation? So we're going to write CH3COO minus aqueous plus H plus. And that's going to form CH3COOH. It likes being in that molecular form. But what else do we have here? We have OH minus. And so the OH minus ions are going to be in solution. The H plus ions have been removed from solution by this reaction. In terms of Le Chatelier, what's going to happen is there's going to be a stress on the system. The equilibrium is going to try and address that stress by making more H plus ions. So the equilibrium is going to favor the forward reaction. By favoring the forward reaction, more hydroxide ions are going to be made as well as H plus ions. And because there are a lot more hydroxide ions being made, that pH is going to be greater than 7. So that shows you what is happening in this particular reaction. So the salt that is formed from a strong base and a weak acid is going to give you a salt which is slightly basic. Let's continue. This question is fun. I love this question. It's a whole lot of stoichiometry all thrown in with our knowledge of acids and bases. So we are given an element X which is unknown. And this learner wants to identify what element X is from this compound, XHCO3. So we recognize this as a carbonate, a hydrogen carbonate. So what is that going to be? So a hydrogen carbonate, if we think back to our list from the big ideas, is going to be a weak base. How does she do this? How does she carry out this experiment? She dissolves 0.4 grams of this unknown X substance in 100 centimeters cubed of water. I'd like to highlight that for you. So we know that when we're speaking about volume, we're speaking about decimeters cubed. So these values, if they are given to us in centimeters cubed, have to be converted into decimeters cubed. She then titrates, okay, so the word titrates, we know that this is a technique when we take an acid and a base and we titrate them together and there's a neutralization reaction. All of this solution with 0.2 moles per decimeter cubed of hydrochloric acid. So we know that HCl is a strong acid. Okay, so what's happening here? We've got a titration happening. I'm going to draw a little picture so that I can sort it out in my mind. Let's say that she puts the acid in there, and that's HCl, and that's a strong acid. And then in her conical flask, she has got a solution here, and it is of this XHCO3, and that is a weak base. She uses an indicator methyl orange during this titration. Okay. The first question is, calculate the pH of the hydrochloric solution. Well, that's easy. We know how to do that. We're going to use this formula, and we are going to check out what the concentration is that they give us. So they give us a concentration of the hydrochloric acid being 0.2 moles per decimeter cubed. That's easy, that's all we need. So we're going to substitute that in to our equation. We use our calculators to find the logarithm, and we come up with an answer of 0.6999, which we can round off to 0.7. Is that the correct answer? Let's check. Well, hydrochloric acid is a strong acid. That means it needs to have a pH between 0 and 2. Is our pH between 0 and 2? Absolutely, it's 0.7. That means that the hydrochloric acid is a strong acid. So we've got the correct answer. Let's carry on. Give a reason why methyl orange is a suitable indicator for this titration. Now, we've got three kinds of indicators. We've got bromothiamyl blue, we've got phenolphthalein, and we've got methyl orange. Bromothiamyl blue is an excellent indicator to use when we've got a strong acid and a strong base. Why? Because the end point is around about 7-ish. And that is where neutralization happens for a strong acid and a strong base. But when we have a weak acid, strong base, and a strong acid, weak base, our endpoint doesn't lie there. We've discussed this, that when we've got a strong base with a weak acid, the salt that is going to result is going to be slightly basic. And so the endpoint is going to be just bigger than 7. So if we look here at phenolphthalein, we see that its endpoint is bigger than 7. So that we would use when we have a titration of a strong base and a weak acid. But for this particular reaction, we have HCl, which is a strong acid. What does that mean? It means that the salt that results is going to be slightly acidic. So will our endpoint be lower than 7? Let's check it out from the table. Yes, it is. It's going to be lower than 7, and so this is the correct indicator to use. Give a reason why it is a suitable indicator, methyl orange, for this particular reaction. Well, we need to say that we're using a strong acid and a weak base in this neutralization reaction, and so the end point is going to have a pH which is less than 7. Okay, now 2.1.3. At the end point, she finds that 20 centimeters cubed, again we've got the centimeters cubed, of the acid neutralizes all of the hydrogen carbonate solution. So this is telling us that the HCl is in excess. So if all of the hydrogen carbonate solution is used up, it means that the acid will be in excess. There's a balanced equation, it's given to you, and we have to identify the element X here. Now, the only way we can identify the element X is by finding out its relative atomic mass. That's the only way we can do that. So our end goal is to find the mass. What do we have though? We've got concentration of HCl. We've got volume of HCl, which is being converted into decimeters cubed. And we have got an initial mass of this unknown solution, unknown substance, the hydrogen carbonate substance. And we also have got a ratio. So we're reacting the HCl, the acid, with this weak base, and the ratio is 1 to 1. So it means that 1 mole of hydrochloric acid is going to neutralize 1 mole of this basic substance. That's really good for us, this mole ratio. Here we go, here it is here. So we're going to find out how many moles of hydrochloric acid has reacted. We use this equation, C is equal to N over V. You find it on your data sheet. We substitute in the values. We know that the concentration is 0.2 of the hydrochloric acid. We know that the volume that was used is 0.02, and we end up with an answer of number of moles is 4 times 10 to the minus 3. So we're now going to calculate the mass, not the atomic mass, but the molecular mass of this unknown substance, which is the XHCO3, because that's the thing that's reacting, right? So we pop it into this formula again from our data sheet. We know the number of moles because the ratio is 1 to 1. We know how much mass is being used. We were told it's 0.4, and we end up with a molar mass of 100 grams per mole. That is of the entire substance, XHCO3. Now we've got to find out what is the X, just the X. So we are going to calculate the molecular mass of this whole thing. We get from our periodic table the 1, the 12 for carbon, the 48, which is 16 times 3, and we find out that the rest of that molecule or substance is 61. If we work that around, we end up with a mass for X of 39 grams per mole. And if we check our periodic table, we will find that that is the atomic mass of potassium, and we have solved our problem. Right, grade 12s, that's all we have time for today. I hope to see you next time.